Hi everybody, this is Julian from Arcee. In this video, we're going to dive deep into Arcee Fusion, a model merging recipe implemented in our mergekit library. So first I'll give you a high-level explanation of Fusion, and then looking at the code as well as animations that I built, we'll look at every single step of the Fusion process, explaining everything in great detail. Finally, I'll run an example of Arcee Fusion with the llama models, and using a small tool that I wrote, we'll inspect model layers to see the differences between fine-tuning and merging with Arcee Fusion. Okay, this should be fun. Let's get started. Before we dive into model merging, let's talk about a common problem when fine-tuning models with supervised fine-tuning. And that problem is catastrophic forgetting. Catastrophic forgetting is a common reason why fine-tuning projects fail. And in a nutshell, the issue is that the fine-tuning process destroys the knowledge of the original model. So when we run supervised fine-tuning, we start from a base model and we work with one of our good data sets to fine-tune the model, and there's nothing wrong with that. However, in the process, instead of getting a fine-tuned model which maintains all the knowledge from the original model, adding specialized knowledge and task-specific knowledge, we often end up damaging or destroying general knowledge present in the model. And the reason why this is happening is because of what I call spurious updates, where fine-tuning updates every single parameter in the base model, even those who are not important, even those who are unrelated to the task. So model merging is actually a better solution to model adaptation. And I've covered model merging before. We start from maybe two models, merge them into a single one, preserving original knowledge and combining the special abilities that the two models had. So yeah, model merging is awesome. You don't need datasets, you don't need GPUs. It's a fast, very cost-efficient process, and you can even run it on your laptop. But there are plenty of model merging recipes, and it's not always easy to get the performance that you want. So let me talk about that for a second, and I'll introduce Arcee Fusion too. Model merging is a simple process, and writing the configuration files for the merging recipes is equally simple, but sometimes things don't work out. So let's look at an example where we start from a base model which has very good general purpose performance and that you want to improve for specialized task performance. So usually you do that through fine-tuning, as we discussed before. And yes, fine-tuning will improve the specialized task performance, but it may hurt the general purpose performance, and generally the model can be a bit unstable. So a common technique is to merge the two models to try to get the best of both worlds, to get strong general performance and strong specialized performance. But sometimes you get neither, and you get a worse model than the original two models. That's where Arcee Fusion comes in. It's a more efficient merging recipe that will only merge important parameters. And we'll explain in the rest of this video what important parameters are and how we can find them. So now we're going to start diving deep into Arcee Fusion. I would encourage you to read the code. It's actually fairly short. I wouldn't say simple because there's a bit of math involved, and I'm going to break that stuff down for you in the rest of the video. But definitely you should take a look at the code, which you'll find in the mergekit repo. And if you just go to mergekit and merge methods and Arcee Fusion, that's where you'll find it. As you can see, it's about 100 lines of code, so not a ton of code, but some of those lines are a little difficult to understand. So feel free to read the code before watching the rest of the video, or read the code along as I explain the different steps. Your choice. Okay, let's dive into Fusion. In the introduction, I mentioned that Arcee Fusion only focuses on merging important parameters. And that's really the key here. We saw that fine-tuning often fails because we're tweaking every single parameter in the model, every weight. So Fusion doesn't try to do that at all. Fusion will look at the difference between the base model and the fine-tuned model, and it will analyze those two models carefully to look at all the updates and decide if they're really important or not. And if they're not, they're going to be discarded, and only the important updates will be merged. So in the end, we'll update fewer parameters in the base model, maintaining more of the general knowledge that the base model had, and adding only updates to those parameters if we decided that they really matter. And hopefully those will have the specialized knowledge and the specialized behavior that we want. So that's really what Fusion is in a nutshell, trying to minimize updates to the base model to preserve as much of the general knowledge as possible, and only applying updates when they're deemed important. So I guess the question we need to answer now is, what is an important update? How do we figure that out? How do we identify them? And then how do we apply them? And that's what we're going to see in the rest of this video. First, we need to understand what is an important update and what isn't. Okay, so when comparing weights for the base model and the fine-tuned model, we need to understand if an update matters or not. So the first step is very simple. We're going to compute the difference between the base parameters and the fine-tuned parameters. So just plain subtracting one from the other, and we take the absolute value, which gives us the magnitude between the changes for all those parameters, and they're all positive values, of course. So once we've done that, we're going to keep those magnitudes, put them aside, and we're going to run a different process. We're going to analyze the distribution of parameters for the base model and the fine-tuned model. Okay, so we're going to apply the softmax function to each row of each tensor in the two models, turning the parameters into a probability distribution. Okay, so for each row, we're going to get a base distribution and a fine-tuned distribution. Once we've computed the distributions for each row in the base model and the fine-tuned model, we used KL divergence, a mathematical formula, to understand how similar or how different those distributions are. Okay, so KL divergence is a value between 0 and 1. 0 means the distributions are extremely close. 1 means they're extremely different. Okay, so for each row of the models, we have those KL values. And now we can apply the Fusion formula. And the Fusion formula factors in two things. It factors in those magnitude differences we've computed, as well as the KL divergence values. By factoring in the magnitudes and the KL divergence values, we can capture the local changes, the tiny changes that happen at parameter level through magnitudes, and the global changes that are represented by differences in the distributions. And so we have different scenarios. If those updates are just random noise, we'll have very noisy magnitudes but low KL divergence. The distributions will be very similar. So those parameters should be low importance. On the other hand, if we see significant differences in magnitude as well as significant differences in distribution, we can see that these parameters, these rows, are probably high importance on the local level and on the global level. And if we see low values for magnitude and low values for KL divergence, then again, this is probably just noise or tiny changes that we don't need to account for. So that's importance scoring. And you can see how important it is to combine those local differences and global differences. Local only would miss the big picture. Global only would miss tiny nuances in parameter updates. And so by combining those two metrics, we get a better understanding of what really changed when we fine-tuned the model. Thanks to importance scoring, now we have a better understanding of what really changed when we fine-tune the models. So the next question is, what do we keep? Where is the threshold for updates we want to keep and merge, and updates we just want to discard? Okay, and that's what we're going to see now. Of course, we can't come up with a general value that would work across all Fusion jobs. We need to find the threshold for this particular job, for this base model and this fine-tuned model. So we have what we call dynamic thresholding. So let's see how we can find what those thresholds are. So once again, we're going to take all the importance scores for all the model parameters, and we're going to compute a distribution. Okay, so we're going to turn all those values into a statistical distribution, and we'll see that a lot of updates actually have low importance, while only a fraction of those updates have a high score. And those are the ones we want to keep. But again, where do we put the threshold? So we're going to apply quantiles. So we're going to break down that distribution into 4 quantiles. And those quantiles will help us find out what the thresholds are. So let's look at a sample distribution where, again, we have a lot of importance scores with tiny values, the red ones, and just a few importance scores with high values, the blue ones. So here we have Q25 equal to 0.12, meaning that 75% of parameters have an importance score lower than 0.12. And we have Q90 equal to 0.78, telling us that 10% of parameters have an importance score higher than 0.78. So these are probably the ones we want to keep. So instead of just relying on those quantiles, we're going to run something called IQR, interquartile range analysis, which is a formula where we look at Q75 and apply an outlier factor. And so we compute a new threshold, and then the final threshold we apply is the min of that value we just computed and the Q95. So in this case, it would be, let's say, 0.89. Okay, so any parameter with an importance score of 0.89 would be considered as an important update. So the next step is to look at outliers. Outliers are generally not what we want, but in this case, they are the ones we want. So any of those very high importance parameters are the ones we are going to apply. And generally, it's really a fraction of the model, and they have crazy high importance scores. And the goal, again, is to focus on those most important changes and ignore anything else. And thanks to this dynamic threshold technique, we can adapt to very different fine-tuning jobs. For example, if you do very dense fine-tuning, you'll have a lot of changes, and it's likely that the threshold will be a little lower. If you did just a tiny bit of fine-tuning, you probably just updated a few parameters, the important ones, and the threshold might be higher. And obviously, you could have middle-of-the-road scenarios. So again, this technique will guarantee that we find the right threshold no matter how that fine-tuned model was actually trained. So as you can see, we have a pretty robust approach here where by computing distributions, computing quantiles, figuring out thresholds, we can really adapt to this specific scenario you're working on. Okay, this step was a little bit crazy, I'll give you that. There's a fair amount of math involved, so take your time, break it down, look at the code. But really the important thing is to understand that we're analyzing the distributions to find out where the threshold is for important updates versus non-important updates. Okay, the worst part is over. It's easy from now on. So now let's see how we apply the updates, and then we'll do a demo. So now the math pays off because we have the threshold to use, and we can just decide what to apply and what not to apply. And we'll define a mask to select the parameter updates that we want to apply. So that's very simple. We'll look at all the important scores. Anything higher than the threshold goes in, anything lower stays out. Okay, so we define the parameter mask or the parameter update mask based on that. Okay, next we can select which parameters in the base model need to be replaced by their fine-tuned equivalent. Okay, so just looking at the mask, we cherry pick the fine-tuned parameters that go into the merged model. And if they're not selected, we keep the base parameters. And that's how Arcee Fusion works. Okay, we just select what we want from the fine-tuned model based on the mask itself, based on the important scores, and we just select what we want. At the end of the day, we only keep what matters. We preserve the fine-tune capabilities and the base knowledge, and we avoid averaging just for the sake of averaging. Okay, let's quickly recap everything. Take a quick look at the code. So starting at the execute method, so we load the tensors, we compute the importance scores, then we compute the dynamic threshold. Once we have the threshold, we compute the mask. And once we have the mask, we actually merge the two models, right? And it's not that difficult. And if you want to double click on each function, you'll see it exactly works the way I described, hopefully. Okay, let's do a quick demo now. So here's my Fusion example. I'm gonna fuse Llama 3 SQL Coder 8B, which is a variant of Llama 3.1 8B, right? So the config file couldn't be simpler. Here's the base model. We see it here again, and this is the fine-tuned model we want to fuse, right? That's all there is to it. Okay, so let's go and fuse it. So this is how we do it: mergekit-YAML, config file, and an output directory. And it will run for a minute or two. I'll pause the video and I'll be back in a sec. So Fusion is done. It took about 4 minutes on my Mac, so still fairly fast. Okay, so now we've fused those two models. So as a final step, let's compare the fused model with the fine-tuned model. And to do this, I'm gonna use a small tool that I implemented in mergekit. The pull request is outstanding, but I'll include it in the video description if you want to grab it. And what we're gonna do here is basically compare the weights between the base model and the fine-tuned model. So see how many are actually different. And we're going to do the same between the base model and the fused model. And we would expect to see much fewer updates. Okay, so let me run those tools and I'll show you the results. Okay, so this is how the tool works. mergekit-diff, base model, fine-tuned model. Let's launch this. And you can also do base model, fused model. Okay, so what the tool does is for each tensor in the two models, it will load them. It will compare how many weights are different. So we'll get some stats, and it will also compute KL divergence on those tensors. So again, that'll give us another idea of how different the distributions are. Okay, so it will run for a minute. Let me pause and I'll show you the results. Okay, so looking at the analysis between the base model and the fine-tuned model, we see that on average, 98%, almost 99% of the weights are in each layer are different, right? And the median is 99. So again, another proof that fine tuning will touch absolutely everything in the base model. The minimum difference was 81%. So no layer untouched, and almost all the layers are completely updated. Okay, and we see again KL divergence values. So looking at the difference between the llama model and the fused model, we can see that the average difference is only 10%. So we can see fusion is really doing its thing. It's discarding a ton of updates from the fine-tuned model and only keeping, in this case, 10% of the updates, so the most significant ones. And we see some layers are actually unmodified. Okay, so that's really what fusion is all about. So think about all the noise, all the tiny changes that are really irrelevant and that are probably damaging the model. This is really what fusion does. And when we look at KL divergence, we can see that it's an order of magnitude lower than in the previous example. Okay, here we had, a median was 0.001 something. Here, it's 0.001 something. So what that tells me is we reduced the difference between the distribution of the base model and the merge model by a factor of 10. Okay, so distributions are much, much closer when you use fusion than when you use, I would say, traditional fine tuning. And so chances are you will preserve more of the original goodness of the model. Okay, so the last thing we should run, but I'm gonna stop here in the interest of time. I'm sure you had enough. So as an exercise to the reader, it'd be interesting to run evaluation on those two models. So run some general purpose benchmarks to see if the fused model is actually closer to the performance of the base model in terms of MMLU and all those benchmarks, and also maybe run a code or a SQL benchmark on the fused model to see if it's performing better than the fine-tuned model. Okay, so left as an exercise to the reader, and if somebody actually does it, I'd love to hear the results. I may do it as well, put it on the old to-do list. Okay, so my friends, if you made it this far, I salute you. Congratulations. This was an insane one. It took me a crazy amount of work with the animations and everything. I hope you liked it. I hope somebody's still watching. Leave a comment if you liked it. If you like the animations too. Thank you so much for watching, and more coming as always. Until next time, keep rocking.